Hello and welcome to the Side One YouTube channel. My name is Ray, and in this video we're looking at a new project that's been on my mind for quite some time now, and I'll just go back to the ground roots. So back when I was doing my electrical apprenticeship in the late 80s, I purchased a TRS80 Colour Computer too. Those who are familiar with the computer would know that it came with 16 meg of RAM and 16 kilobytes of RAM and ran at 1 megahertz. The truth of the matter with the way it was set up, it used a synchronous address multiplexer that actually had a 4 megahertz crystal on it, and that downsampled the clock to 1 megahertz for the processor and multiplexed the RAM to the video processor. The video processor would then output video to a TV. In some circumstances, you could reconfigure the SAM chip to ignore the video coprocessor and just clock the CPU, which was a 6809E, at 4 megahertz. And one project I came across and trialed, and it sort of worked, was a speech recognition program. So when you spoke, it would switch into the 4 megahertz, so boosted speed, for a short time while it processed the audio that it captured, and then it would switch back and show you what it recorded and converted into text. It had a 50-50 accuracy with me, but it was the beginning of speech recognition on a very small system. Now, I had upgraded the memory on my computer at the time to 64K, but we're talking very small amounts of RAM by today's standards. Now, when you look at microcontrollers, even the Arduino Uno had more RAM in it than what that Coco had. And it runs at 16 megahertz as opposed to between 1 and 4 megahertz for the 6809E. And then roll on even further, and the Raspberry Pi Foundation released the Raspberry Pico. Now that's been out a few years now, and they do have a newer chip and breakout board called the Pico 2. But working with the Pico 1, or the RP2040, I actually have a pair of these on hand, and so I've been working on breaking the project up and trying to get it better. Now, back on the old Coco, the audio input was not what you would call the best. It used a 1-bit input, and so it was pretty ordinary audio it was recording. Using today's technology, we can do much better. So what we're looking at is taking 3 microphones, connecting it to a Raspberry Pi Pico on the 3 available analog inputs, and capturing all 3 at once. The microphones will be arranged in a linear array at 50mm separation between them. And using this, we can use what's called beamforming. So we capture all 3 microphones at roughly the same time, and then we will delay different microphones to form beams, summing together at different time offsets. And this helps narrow the range at which it will actually hear audio, as audio will come in, hit the first microphone, and then by the time it hits the second microphone, the frequencies that it's hearing will tend to want to cancel out each other when they're summed together. And we do this over 3 microphones in total to give us a fairly good cancellation of noise from other directions. By doing this, we can actually create beam-formed channels, so that we can have up to 5 channels from 3 microphones that correspond to roughly minus 60 degrees, minus 30 degrees, 0, which is dead ahead or perpendicular to the 3 microphone array, then positive 30 degree and positive 60 degrees. Then taking that on, I had a look at how does the human ear work and how does the human brain interpret speech. The human ear is an amazing piece of engineering, biological engineering that is, and it's pretty much a analog to spectrum analyzer all in one little neat unit, and it sends a stream of pulses, which we call spikes, from the ear to the brain as parallel information. Now, a lot of people don't realize it, but the brain is actually a very slow processor. It's not actually running that fast. So the information coming in as a series of pulses is actually showing us pulses of frequencies much higher than what the brain can process. So by breaking it down into a frequency spectrum, the brain can actually run it through its neural network. So for that, I need to take each of my beam-formed audio inputs, which are an analog input, and we're going to convert that into frequencies. And for that, we're going to use a 256-point fast Fourier transformation and pulling out 20 different frequencies between 500 Hertz and 5000 Hertz, which is roughly where speech resides. Then, because this is already doing a fair bit of work, because we're doing 5 at once, we're going to pass that information on to another stage further on, which will be another Raspberry Pi Pico or maybe a 2350. Because of the sheer workload involved, I'll be using multiple second stages. So one for each beamform channel. So we're going to send this out using I2C and pass it through. The Raspberry Pi Pico, or the RP2040, is a pretty cool little microcontroller. It's dual core, running at around about 130 megahertz, which is way faster than the original Coco and a way more processing power. It also has an ADC, or analog to digital converter, built in, running at 12 bits. And we can run it up to quite a high sample rate. With that in mind, we're going to capture 3 channels, and we can only do this one at a time. So we'll set up a round robin and capture those channels into a FIFO, and then use the built-in direct memory access or DMA transfer to transfer those captures into memory that we can then access. Once we've done that, we'll do the beamforming, and with that we will pre-calculate what our delays will be. So each sample, and we'll be taking samples at 16 kilohertz. We will take each of the samples and we'll beamform to create 5 channels. Once we've completed the 5 channels, we'll hand off the workload now to the second core, where we will do a 256-point Q15 fixed point fast Fourier transformation. Now, the reason for doing it that way is it's much faster than a traditional fast Fourier transform, in as much as we're not doing floating point maths, and it gives us roughly a 10 times improvement in performance by doing it that way. And any savings I can get, I'm going to grab at this stage, because we are really pushing this little RP2040 to its limit. Once each channel is processed, it will pass on to, or back to the first core, or core 0, the completed FFT, and that will then pass it on to the appropriate I2C channel. Now I've chosen I2C channels 0x60 and above for my 5 channels. I've still got to write that next stage or create that next stage. One of the things we're going to do is, if a stage fails and stops receiving data, stops communicating, then we're not going to get an acknowledgement signal on the I2C bus when it sends. So we're actually going to look at that failure to respond and light up an output. So we've defined a few pins. If I scroll this up. So pins 26 to 28 are our 3 ADC or analog to digital converter inputs for our microphones. 8 and 9 are the I2C, SDA and SCL, so serial data and serial clock for our FFT exports. Outputs on GPIO 0 through 4 are our error signals. So if a I2C device at 60 through 64 fails to respond, it will light up an LED connected to one of those pins. And to help with debugging and to ensure that everything is working, we've defined GPIO 5, 10 and 11 for debug timing signals. And I can actually show you what that looks like. And this is an example of a timing debug. Now I'm using my older logic analyzer for this because it's easy for me to set up and I know how it works. So what we have here is channel 4 is GPIO 5. Channel 2 is GPIO 10 and channel 3 is GPIO 11. And channels 0 and 1 are my I2C. So we can see the I2C pulses. These are coming back with a fail, and you can see that on the side over here. No acknowledge because I haven't actually got anything connected to them yet. But what we're seeing is this channel 3, the debug is when it starts to process the fast Fourier transform. But let's go back to the start. When the DMA has finished transferring our samples from the microphones into memory, we then have a series of pulses which indicates that it is processing for beamforming, and it's creating each beamform channel, so 1 pulse per beamform channel coming through on channel 4. When it's finished doing that, it sends the data to core 1. So this is occurring on core 0, and when it's completed, it passes it on to core 1. Once the data is available, we turn on GPIO 11 to show that we are now processing the signal. As we do each channel, we turn the output on until we're finished processing the fast Fourier transform for that channel, and then we drop the signal and we pass that completed packet for that channel back to core 0 so we can process the I2C. While core 0 is processing the I2C, assuming that it was responding, it would continue to pass data through this area. It starts working on the second channel, and it repeats this process until it's done all 5 channels. When it's completed all 5 channels, GPIO 11, so that's here, will drop back down to 0 to show that it's idle. Roughly 62 times a second, I think I worked it out at. I do have a timing that I can set up. So if I go to here and click on my second marker and go to here, we can see that we're getting 16 milliseconds of timing, which equates to about 62.5 hertz. So we're getting 62.5 updates per second from this process of capture. And the idea is that will pass that information on as a series of bins. So let's go back to our program. Once we've converted all of the data, and I've got some fairly good description of how it works here. Once we've converted it, we will send all the data for each channel to an individual device down the track, and it will be another RP2040 or Pico. So this is only the first stage. What I will probably do is create a test program that I can run on a second Raspberry Pi, Raspberry Pico, just to test a channel and confirm everything is working as expected and that I'm getting the data that I expect to see. Now, just so you can see it, I'll turn on my camera and I'll show you what I've got. Actually, I might be able to do that here. Okay, so this is my Raspberry Pi Pico. As you can see, I've had this one for quite a while now. I only pulled it out of its packaging yesterday. It's the first time I've gotten close to getting this program to work. It's taken a lot of debugging. I did try out Copilot for this project on Visual Studio Code just to see what it was like, and most of this code was created with input from me on how to make this work and to go through all of the debugging. There was a lot of debugging to try and get this to work. I've spent a couple of weeks on this already. So the captures you saw were actually captured off this using this logic analyzer, and I've got it working. I'm happy with that. I'm going to program up a second Pico and I'll connect the wires just to make sure everything's working, and then we'll start on the next part, which is trying to capture the data or trying to make sense of that audio data. So I've got some thoughts on that, and my thought is AI in its current form is actually getting very good at image recognition. In fact, capturing a 16 by 16 image of handwritten numbers is a pretty common and easy thing to do with a very high accuracy. I want to actually go a little bit further than that and break it down into trying to capture phonemes or phonemes. Now, phonemes are the components of words. So you'll use multiple phonemes in series, including a silence, to create a word, a spoken word, and a break between it and the next word. And then a longer break is essentially the end of a sentence. So what I want to do is convert those frequency bins that I'm getting out of my FFT, and in my second Raspberry Pico, I want to capture that as a flowing buffer and capture up to 1 or 1.5 seconds worth of this 20-bin 16-bit data that I'm getting. This could then be viewed as a 20 by probably 100 sample image, and it'll be a grayscale image where the value of our bins is how bright the pixel is. Then use a liquid spiking neural network to convert that into 44 phonemes. Then I can pass that on to a third stage, which will read the phonemes and convert that into English text. Now, the beauty with, if I configure that that second stage, to use up to say 120 or 140 phonemes, that covers pretty much every language in the world. And then that means we can actually make our third stage convert that into other languages. So this while I'm starting out as English only, in theory, can move into other languages such as French, German, Italian, Indian, just as an example. There are quite a few languages spoken around the world, and it is a very large community in the robot world. So making it so it can expand into all languages is actually a good idea in my view. So to see when all those projects come up, don't forget to click on like, subscribe, ring that notification bell. It's a form of support that helps the channel a great deal and costs you absolutely nothing. If you'd like to support the channel further, I do have both Patreon and YouTube membership, and you can join my VIP patrons Go Lucky, Jeff Jerd and Kuriz Katini, my Builder patrons Al Morales 45, Andrew Cardone and Agar 69, and my YouTube member Joel Huxwell in helping support the channel. There will be a link in the description. If you've got any questions, feel free to drop a comment below or drop into my Discord. I will be setting a section up just for this project, and ask a question in there and I'll do my best to answer it. All these files that I've created for this will be available on my GitHub, and there will be a link for that in the description as well. And we'll see you in the next video.